Hi everyone, today we're going to talk about the isolation of cholesterol from gallstones, something you're going to be doing in your lab, and this is a really classical organic teaching tool to introduce you really to chemical biology. Chemical biology is a very important field these days where chemists create tools and methods to help biologists and biomedical researchers. So you're going to be using basic principles of organic chemistry in order to isolate a natural product from a natural source. The structure of cholesterol is on the upper left, and you see the structure of three other compounds, one just to the right of it, cholestanol, and the two below that contain double bonds. And it turns out that cholesterol is typically isolated along with these very structurally related three other compounds that are present at trace levels a few percent. And so the basic idea here is to see how we can isolate cholesterol from these very structurally similar compounds which have similar properties to cholesterol to begin with. Now, in spite of its bad reputation, cholesterol is actually present in all animal cells and serves some good purposes. You can read about some of the bad things in your lab manual, but it's used in cell walls. It's a basic structural component of cell walls, and it's required for the formation of the myelin sheath that covers nerve bundles. It's also a precursor, or that is a substrate, for a transformation, enzymatic transformations in the body, metabolic transformations to other important steroidal hormones that afford a variety of beneficial function in the body. So again, cholesterol isolated from natural sources is generally contaminated with a few percent of these other three structurally related compounds. And so the challenge in this lab is how do we isolate pure cholesterol from these other three? Of course, having a much larger percent of cholesterol as compared to those other three compounds makes things simpler. However, it's still challenging, and we're going to show you how this is done. So it turns out that the chemical reactivity towards bromine is different for cholesterol than it is for those other three compounds shown. The compound on the upper right on the previous slide doesn't have any double bonds, so it's obviously not going to dibrominate. The other two compounds do have alkenes. However, because of sterics and the way the steroidal ring is structured, and you can see this if you try to draw the six-membered rings, for instance, as chairs, etc., and so on, you'd see that it's more difficult to add bromine atoms. And so bromine atoms to those other two compounds on the bottom left and right on the previous slide. So those other two compounds get oxidized by bromine, and they form dienes and trienes. So in other words, they add more double bonds and through an oxidation process that we won't go into. Now, why do we do this? Well, it differentiates cholesterol chemically from those other two compounds. And that turns out to have a very beneficial effect. The dibromide derivative of cholesterol is very insoluble in the reaction solvent, so it precipitates out, and you can filter it off, wash the precipitate, and those other three impurities after bromine is added, they still remain in your filtrate. So this is how we actually isolate the cholesterol dibromide, not cholesterol directly, but we isolate the cholesterol dibromide from the other components in the mixture. And then we can convert the dibromide of cholesterol back to cholesterol, and notice the top arrow, by adding zinc in a reductive elimination mechanism. And that's something you're going to do. And we think of the mechanism as shown there, where you have diaxial bromides, and the zinc comes in and it does an elimination. It's very analogous, at least we think of it as analogous to a standard E2 elimination that you've studied in sophomore organic lecture. It's different though. It's different in that we're not exactly sure the mechanism, and it involves a redox process, but still it is analogous in many ways to the E2 type elimination that you've seen before, but it is called a reductive elimination because of the change in the oxidation state at zinc, etc., and so on. Okay, so here are some things to consider. Why are diaxial substituents needed in the reductive elimination and in the E2 mechanisms shown on the previous slide? This is review. It's something that you've seen before in organic lecture, but it's important in the current in the current experiment because you're going to have diaxial bromides in cholesterol in order to do the reductive elimination, apparently. So draw the dibromination mechanism for cholesterol, and this is interesting. You know how to do a dibromination of an alkene via the addition of Br2, but what you should consider is what side the first bromine is going to attack on the cholesterol molecule, which face of cholesterol will be attacked first and why. And then where does the second bromine atom add? Which carbon gets the second bromine atom? Again, this is review, but seeing this in the context of cholesterol is really helpful, and it's a really great way for you to review some basic concepts and apply them in a real world experiment. Okay. Also, what structural features does cholesterol possess that classify it as a steroid? What does a steroid? What's the fundamental things that a compound has to have in order for it to be put into the steroid family structurally? Is cholesterol a lipid? What's the definition of a lipid? And of course, for each step in your procedure, make sure you can justify the purpose of each solvent and reagent that's used in each purification step in light of the differential solubilities, particularly of your products and impurities. So this is an interesting lab, and good luck and have fun isolating cholesterol.